So this is a project I'm working on now for quite a long time. It's Chris Wysotsky and Eddie Zehnder. And it came out of another project. I mean, it's related to another project with Eliashberg and Leventhal. So this one here in 2000, we wrote some kind of a propaganda paper outlining the symplectic field theory. So we didn't claim that we have any proofs, but we described how a certain theory should behave, what properties it should have. And symplectic field theory is some kind of a, can view it as a generalization of Gromov-Witten theory, if you want. So then, that in fact had already started somewhat earlier. So actually in 1993, it was already clear that you could do a contact homology if you could resolve all technical issues. Then actually in 1993, we also started developing the analysis which you needed for this. But we had a certain number of side projects as well. And what I'm talking about now is started also around, I would say, about 2003 or so. So now, so what is it all about? So there's a useful philosophy of constructing invariance, geometric invariance. And so you have some kind of a geometric object. And then this usually comes with some kind of a auxiliary structure. So think, for example, of you study a manifold, smooth manifold, auxiliary structures could be Riemann metrics, or you study a symplectic manifold, and the auxiliary structures would be almost complex structures compatible with the thing. And then you make here a choice. And then you associate to this an elliptic PDE. So let's call this choice lambda. And you study an equation, and you sort of count the solutions in a particular way, and then you show that it doesn't really depend on all the choices involved, and it gives you an invariant. So that is the scheme. So now elliptic PDE is, of course, related to studying a Fredholm problem, but in this case, the thing is that I'm writing, it's a philosophy is that it barely works in the obvious way for basically all the problems you're interested in. And the problem are, in general, one has compactness issues. So that means the solution set of this equation you would write down if you come up with classical ideas would not be compact. And then, of course, counting things is not so clear what that would mean. And you have transversality issues. So these are things which usually arrive, and then people spend an enormous amount of time then overcoming this kind of issues to come up with a method of counting solutions which is independent of the choices you involve. Here, counting has to be understood in a most general way. It can be actually counting how many solutions you have, mod sign, or mod 2, or it could be a homology group, any algebraic device you can use to associate to this some, any algebra you can use to associate to this some algebraic expression, which is independent of the choices. So now, so from a classical, so let's assume there wouldn't be these issues. Yeah, so let's assume this philosophy would actually be something you could apply. So then, what would you study? So you would have the following situation, and maybe more complicated geometric versions of this. So you would have, say, a Banach space bundle, and you would have a Fredholm section, and a Fredholm section, so it would be smooth in the usual way. And if you have a solution, if f of x is equal to 0, you could linearize, and this should be a Fredholm operator. Yeah, so everybody knows what a Fredholm operator is. It's a bounded linear operator with finite codimension, where the image has finite codimension, the kernel has finite dimension. So then, a Fredholm section would be a smooth section which at a solution set, if you take a point in the solution set, the linearization, which is from the tangent space of x to the fiber over x, should be Fredholm. So if you assume now that the solution set is compact, let's assume that would be true, then there's this sort of part of the Sartre-Smale package which tells you that if you take a neighborhood of the solution set and take a sufficiently small perturbation which is generic of f, then this solution set actually turns into a nice manifold. So Sartre-Smale would say that for a generic small section S, the solution set of f plus s of x equal to 0 is a compact manifold. Actually, as I write it down here, it's not entirely correct. You would first have to fix the neighborhood of this, because by the section you could create some solutions far away. But if you take a neighborhood of the solution set here and then look for the solutions in here, if the section is small enough, then in that neighborhood of this set you would have a nice manifold. Then if you take a different section and you take a generic interpolation between this, you get a cobordism between the two things. And if you have some differential forms on the space you can integrate off, you get something which is invariant. So now so of course now there are versions of this which would, so let's assume we would never have to face these issues when we want to define invariance. Then of course you might have to look at other situations where these are orbifolds, orbibundle. Then if you want to do Floer, suppose there wouldn't be any difficulties in Floer theory, you would introduce other things, other structures you would have, for example, that a fibered product of the space with itself would be related to the boundary of the space. The broken trajectories. Now if you look at the gradient flow, and you look at broken trajectories, then the broken trajectories are a fibered product of iterated fibered product of the unbroken trajectories. So if you view that the broken trajectories, so let's now assume they're not necessarily gradient like. If you look at broken curves, then the space of broken curves is sort of the boundary, but it's related to the total space by being a fibered product. And this relationship creates a certain amount of algebra, and that Floer theory would automatically come out of this. So what I want to say is, if we wouldn't have this, the Sartre-Smale theory, Fredholm theory, would be more than sufficient, and soft enhancements of this would actually be dealing with all the issues. So of course, this is if we wouldn't have these issues. So now, since we have these compactness issues and the transversality issues, this approach doesn't work. But it would be nice, that was our viewpoint, so HWZ viewpoint, it would be nice if we could actually generalize all the notions, like Banach manifold, Banach bundle, so that you have the same letters there and the same philosophy would work. So you wouldn't have to change the philosophy. So, and in fact, that turns out to be true. The the problem that you couldn't deal with this was rather a language problem with a certain amount of results you have to prove. But ultimately, this philosophy actually works. You can make it work, but the letters then have more general meanings. But you can talk about, you have to generalize the notion of a manifold, to generalize the notion of a bundle, you have to generalize what a Fredholm section actually means. So now there are also other ways to approach this. So one is Kuranishii structures, and I'm not going to talk about it. They are sort of born out of attempts to overcome this. But they break in some sense this philosophy here. So there are some new objects. But I think since this philosophy is really so nice, and I think everybody knows this, I mean, it's a finite dimensional thing, implicit function theorem and so on, generalized. I think philosophically, why shouldn't one take the same philosophy if you can do it by generalizing the meanings of these letters? Okay, so that's... So now, so we have compactness issues, and but what is true is but it's not that bad, but also in these cases, but usually there are good compactifications. So good means, well, depends what that means. We can interpret it. They are not good enough that you can bring this into this thing here. So you could sort of think, instead of studying the problem, I'm starting where I can't do it in this framework. I compactify, and then it fits into this framework. It doesn't. It doesn't fit into the classical framework. Because these compactifications here are so that sort of gut-wrenching for classical analysts. So the thing is, these compactifications, even if they would, you are very far away from smooth analysis in the usual way, in the usual sense. So this new object, these compactified spaces, do not fit nicely into a classical analysis framework. So these compactifications then usually are used as follows. So you study this problem here, and you have a compactness issue. So suppose this is my space X, and here's a solution set, and it's not compact, so the solution set runs to infinity. It might be higher dimensional. Then the compactness says, well, so if you now make this solution set as generic as possible, classically, then you would say get a nice manifold, and then you plug something in from the outside to fill in an end. Now, in general, what you plug in also what you naturally want to plug in or have to plug in also has ends. And then for these ends, so you plug something else in, but fortunately there's some energy, and after some time you are gone, you are finished. So these other things you plug in are also solutions of some equation, and they're in general also not generic. So you start here, which is not generic. You have to perturb it to make it looking rather nice, but it's non-compact. So then there's some related equation, and the things you have to plug in are also non-generic, so you have to perturb this. And there's a whole hierarchy, but for some fortunate energy reasons, only finitely many. So you take sort of the highest up problem, make this generic, plug this into the other problem, but which you have, however, to perturb appropriately. Then you perturb that down. Then this have to be plugged into the next thing, extend the perturbation, and go the way down until you have perturbed that problem. Yeah? So you have a hierarchy of problems. You have to, the higher layer you have to perturb, glue this in, but then you have to modify the problem where you glue it in, extend, and so on. So now that is already, when I describe it, it looks already a little bit complicated, and this involves usually a lot of analysis. So now the problem, of course, gets almost out of hand from a logistical standpoint if you start with problems like Floer theory or SFT, where the algebraic structure is based on things degenerating, and you have all this bubbling off and all kinds of phenomenon, and the whole structure comes that you have, in fact, a countable set of such problems which interacting. They're all bad. And each of these problems, however, has to be used to compactify a previous problem after you made it generic. So you start with some strata in the way as I described it, and you get something perturbed, which is good. Now this thing which you have turns out to be showing up in infinitely many other problems, which then you have to perturb. So you see already how the perturbations grow. So there's a lot of things you actually have to control, and it's extremely difficult to talk about this. But so you see, if one would have a more general theory where the solution set would be the compactified space, you would just talk in the usual way about it, which would be a lot faster, like, well, we have this, the solution set is compact, take a generic perturbation, and then it's a smooth solution set. And the fact that people deal with this is in fact that the classical analysis is not so nicely adapted to describing this, the compactification. Also, people like then to take shortcuts and just saying, well, for example, if it's one-dimensional, I don't even want to say that the whole object I get is actually smooth at the interfaces where I stick something in and so on. For certain topological problems, it's usually enough. So that is one of the issues. So so let me now just draw a picture which gives you an idea how the new framework looks like. Then we make then ask me questions concerning what I said so far, and then I start developing and addressing all these things. So in the classical theory, the spaces which you now say in the easiest way are manifolds, and they are the theory which binds together open sets in Banach spaces. That is a theory about things you can do with open sets in Banach spaces. Now, when you, for example, want to describe bubbling off, so a holomorphic curve appears, a sphere bubble appears. I hope that everybody knows this, otherwise we'll come back to this. Then it's not so clear if that actually is a smooth phenomenon or not, but it turns out it is in the right description. Bubbling off is a smooth but generally not generic phenomenon. And how does a space look like near, suppose, so you have a solution set of holomorphic curves and a bubble appears. So then there will be a surrounding space of not solutions which also have bubbles, possibly bubbles. So how does a neighborhood of a noded curve look like? Suppose a piece of cylinder with a sphere bubble on it. So in the neighborhood, there should be also bubbles with different spheres, different cylinders, but attached. And there should be things where the sphere is actually glued into the cylinder. So how does a neighborhood look like? What is a natural model for such a neighborhood? It's an open set in a Banach space. So I'm pretty, well, at least if you have natural requirements, it is not. Actually, it is rather infinite dimensional object of this kind. So take a ball and add the equator to this. So it's an open ball, and I add the equator. Then I add an annulus to this, but it's open. And I add a point to this here, and a point to this, and a loop like this. These are rather the kind of models you would occur where a point like this would be a point where bubbling off occurs. So it's like objects of this kind. Yeah, so suppose a ball, or easier thing here, if I take a disk, two disks, and I attach a loop to this. An open two disk with a loop to this. So if you try to find local models of things you want to describe in relation to the non-compactness issue, then you would have to have a theory which in finite dimensions would rather look like this. This should be a smooth object in your category. A disk with something like this attached. Or an open ball with an annulus attached at the equator, and then something like this attached. So now, if you look at this finite dimensional thing, you could imagine how you can define this by classical methods. You would say, I have this open ball, and I can attach this annulus by actually sticking it in. So I need an annulus, a little bit longer. I actually choose an embedding into this thing. So the annulus is a little bit bigger and goes into this thing. Then, of course, it doesn't matter how far it goes, so there's some equivalence relation. Yeah? And then you have to stick in this interval here. And in some sense, what matters is the infinity germ, the infinity jet, how you stick this thing in. That would be a description. You could, of course, stick it in like this or like that. Yeah? So there are different ways how you can do this. But you see that the description already is cumbersome of this. And it's as cumbersome as here. That is what you do here. Something goes away, you stick something in. You take another space. You do it only on the level of solution sets. Stick something in. Stick something in. So it's the same thing, and that explains you why it's sort of so cumbersome, because already in such a simple situation, which is quite similar to this, it's cumbersome to describe it. So now it turns out that this polyfold theory actually generates new local models for smooth spaces, and the formal, so there's a very appealing construction of new smooth models for local models for spaces. So instead of just having open sets or say half spaces, open sets and half spaces and so on, you have a new library of things, and you can local models, and you can talk about smooth maps between these local models. You have this chain rule. And if you can do this, you just take any recipe ever invented in differential geometry and just get differential geometry with new local models. Of course, new local models might allow you to do a lot of other things as well, but you definitely recover differential geometry. And that is, and the language will be precise, to describe these things, the language is precisely the same. These things will be manifolds in this new category. And they're given by taking an atlas of smooth charge to the local model, the transition maps are smooth. So the language is completely the same as before, except you have this, guys. Okay, so let's...
For the analogy there, so in which direction are you moving?
Yeah, so that is debatable. It depends. That's actually debatable. So in general, okay, so if you do Floer theory, then you would say that a broken trajectory, so suppose you consider the space of passes. Let me take the right. Consider the space of passes connecting 2 points. And then there's another point, and then if they approach this, you would get a broken path. So then you would say that the broken passes should be sort of the boundary. You know, if you have the right topology, let's say the non-broken passes are open and dense, and that is sort of the boundary. So the boundary, in any common sense theory, seems to be usually one dimension less than the other. Now it turns out that in this theory, the boundaries can be actually much higher dimensional than the other things. So that is what happens. So in some sense, I would say if you move to the boundary, you move in that direction, if that would be infinite dimension. Is there any other? So it's a so the point of this was so far to say something about the philosophy, what we want to do. Is the general direction clear? Katrin? Or yeah, I think you take so you could take a space of CK section, K sufficiently large, that's a Banach space. And then you get the solution set would be CK manifold. And then you make a C infinity small perturbation of this that will not destroy this. And then you get a smooth manifold. Or you take this Floer epsilon type thing. No, because you start with a compact solution set, so near every point, the Fredholm thing has a normal form. It's an isomorphism plus something finite dimensional. It just doesn't move. You get out of this local compactness. So it takes a neighborhood in such a way of the solution set that the normal form which you have near point X extends over, so you have a neighborhood there, extends over that neighborhood there. No, it's no. I mean, no. This is no. There's no there. No. I mean, so the question is, if I have a sequence of perturbation and it gets smaller, and I know if xk is in u bar, I have to show that in the limit that this is compact. That the sequence converges, and it would converge to the interior. So that would tell you if the perturbation is small, the solution set in U would actually lie in the interior of U. In U bar would lie in the interior of U if S is small. And for this, you only have to know that, so for every x, you find a neighborhood where you have a normal form for your Fredholm section, for every x in the solution space. Then the solution space is compact, and you take a finite covering of this so that you have the normal forms. And then you have local compactness because you're in one of these model neighborhoods. It's no problem.
Okay, but the only source
No, I mean it's then. I mean I think that is very well known for people who use Fredholm theory. That is so you have some kind of, if you have a Fredholm problem, you have some kind of a local compactness theory. So there are this. By some Russian guys, Borisovich, and so they wrote a survey about classical Fredholm theory and so on. So I think that I'm pretty sure that is in there. So that is rather standard. So if you take a sufficiently small neighborhood of the solution set, then if you take a sufficiently small C0 section of this, then the solution set will actually be contained strictly in the interior of this thing. And then you can take smooth perturbations, take enough perturbations to make, so that you have enough to make genericity. Yeah?
So you said there's two calculations, compactness and universality. Is it fair to say that polyfolds are something that address compactness issues?
No, they're both. I mean, so the first thing is so the current state, and I hope that future with all these bright people here and why with those who are not born yet, will lead to the following. So currently, the philosophy is like this. You want to study a geometric problem. You run into a compactness issue, and you think hard and find a compactification. And the compactifications are usually, they are nice in some way because they compactify the problem, but they are usually difficult to handle in the usual analysis. But as our analysis shows, if you generalize it appropriately, they fit nicely into a picture. And then you show that the original problem which you have can be extended to the space which contains a compactification. And then it's a Fredholm problem. And then our package gives you just the same. Just take a small perturbation, and this thing is generic. So it does precisely what it is precisely this, the Sartre-Smale package which is offers then. Yeah?
So if you want to do this type of theory, there is the amount of smoothness. But now,
Yeah. Yes, that is, I mean, well, that is, well, I can answer this question by adding some more things to it. So if you do Sartre theorem, there are certain inequalities which have to be true that it holds. It has to be sufficiently smooth given what the domain, dimension of the domain, target, the difference. So that still is true in the Fredholm theory. So if the Fredholm index is too big, you need a certain amount of smoothness that you actually have a perturbation theory, which makes things generically transversal. So, so now you could ask, is it possible to make a C0 theory? That's a good question. I would love if that is true. Because then maybe you have less headaches for a lot of problems. But I mean, I thought about it, but I don't know if that's possible. So I have to do a certain amount of smoothness, and then I don't want to be as so I mean, the benefit is that I can say things are generic after just saying I take a generic perturbation. I don't have to worry about what I'm doing. If I'm in the C0 category, then still maybe you could make a solution set C0 manifolds, and they would have a fundamental class and so on. But it would be presumably you have to work hard. I mean, the goal here is not to work hard. After all, again. Yeah, okay, so let me first finish the smooth case, and then I take a break for a day or so, and then I think what I'm going to do with my life. Maybe that's not one of the things, but any other? Okay, so let's now look at where the problems with these compactifications come in. One can isolate it. The word compactification will not appear. But in general, these compactifications create analytical problem of the following kind. So you have a space, you have a Sobolev space of maps on a domain, and suddenly you have a group of diffeomorphisms, continuous, smooth, say you have a family of diffeomorphisms acting on the domain when you change a parameter in a smooth way. But the actions of a smooth family of diffeomorphisms on a domain, this action is never smooth on a function space. It's actually nowhere differential. It's not differentiable at any place usually. And that is why the analysis breaks down, because these compactifications usually have to do with families of diffeomorphisms identifying certain domains and so on. So so the analysis coming from the compactification is usually the one which is non-smooth at all. And that is why then if at some point you had a case where you don't have smoothness, how would you have Sachs-Mehl and this kind of things in this context? Okay, so let's look at some of these issues which would actually arise when you look at certain compactifications. So let's look at the following here. This was already explained by Albers in his talks, but let's look at this again. So we have Rn, and let me assume I have 2 points there. And let me define the space, let's say, of Sobolev AB, which is the following. So these are points in Rn. And what I mean by this, these are maps from R into Rn locally in H2 with an additional property and U minus A and U minus B are in, say, this here is in H2 of, let's say, minus infinity S0 Rn. And similar here. So the map U approaches in backward time the point A, so that the difference between the constant function A and U lies in H2 on that tail end. And in the positive direction, you approach the point B, so that the difference between U and B lies in the Sobolev space H2 as well, on the other tail end. Yeah? So the thing looks like this. So in forward time, this is A. You approach B in backward time. That's the difference between the constant function A and this thing lies in H2 and so on. So you could alternatively write this. If you take a smooth function, which in forward time is B, constant B in backward time is A, then this would be the space phi plus the Sobolev space. Yeah, it's an affine space. Okay, so now on this space, we have an obvious R2 action. By the time shift. So this action is not differentiable at any point. I mean, this joint map is not differentiable. It's C0. It's not differentiable at any point in the usual Freshes sense. You can write down some formal linearizations at a smooth point, for example, but it's not. But if you look at what does differentiability mean in the Freshes sense, it means f of x plus h minus f of x minus df of xh norm divided by the norm goes to 0 if h goes to 0, if the norm of h goes to 0. You can write any formal differential. At certain points, you can write down formal linearizations, but they can never be uniformly approximated in this way. So it's as bad as it can get. So this action is only C0. So now, what is this? What is, for example, the structure of this space? So it should be a C0 manifold, but maybe they already have to work a little bit. But is it better? Is it better than that? So now, so why am I interested in this? Well, because this kind of issues would arise in Floer theory. Floer theory, or if I do Mach's theory as a Fridholm problem, I would have to look at, I would have, say, 3 different points. And I would look at mod R. This would be the things which go directly from A to C, modulo the R action. That could be a gradient line modulo the R parameterization. But here we have a larger class of things. And then I would take broken things. And broken things would be formally this guys. So if I want to have any smooth theory, and this would be the spaces where the Floer thing would be defined on, yeah, then I would have in this theory, this guy should be smooth. So then this would have a smooth structure, whatever it is. This then would be smooth. The product would be smooth if it's a good theory. If 2 things are smooth, the product should be smooth. And then there should be a smooth, so this thing, which should be the boundary, is smooth. This is smooth now at the moment, the disjoint union. And then there should be a smooth structure on the whole thing, which explains this as the interior and this as the boundary. Yeah. So if you want to have a smooth theory, you would have to answer that question. So it's unavoidable to answer that question. In fact, these are the things which always occur in compactness issues and so on. So compactness issues are usually questions like this which arise. This is an example of a group, of a diffeomorphism group acting, the R. Okay, so let me, before I start, write this here, then let me draw another picture. Suppose you have maps on a cylinder, finite cylinder, and you attach a bubble to this. So that means this would be the image of a finite cylinder. Yeah, so I have a manifold M. I look at maps from a finite cylinder, that would be the image, and a sphere, image from a sphere, which is attached at this point. So what should be the neighborhood of this thing? The neighborhood would be some kind of deformed sphere, deformed cylinders, but still attached to this point. But then if you, but the thing should also contain this guys, where this is, where in some sense this thing is being removed, which would have to be viewed as a map from a cylinder. So in this case, you see, we would deal with varying domains. The image of this would be coming from a cylinder, whereas the image of this comes from a cylinder with a sphere attached. So if I want to cover bubbling off as well, I clearly should be able to deal with varying domains. No, well, if you want, you can, but here I would be interested in the things which are detached, where you have a map on cylinders, and in some sense the gradient would blow up near a point, and the image would be very large, and if it completely decouples. No, in this case, no. So that would be sort of something which arises in Gromov compactness. So one also has to deal with varying domains. So there should be a smooth, so what is classically known for a long time is if I have two manifolds, say M and N, and I look for maps from Sobolev class, suppose M is compact, from Sobolev class from M into N, this is a Banach manifold. So now you want to replace M by things which can change. But if things can change, you already have diffeomorphism groups. So for example, think of cylinders of different lengths. Then if you want, then in a chart should sort of look at, would parameterize cylinders of smaller lengths or larger lengths by the other one by taking certain diffeomorphisms. So you see immediately how diffeomorphism actions would come in that question, which is precisely the issue which in a simple form occurs here. So then in symplectic field theory, where we have cobordisms which is split apart at something, we also have varying targets. So we have varying domains and varying targets. So you want to have a theory where the manifold M changes topological type, the manifold N changes topological type, and you have, say, some Sobolev class maps between them, and you want to put a smooth structure on them. That is, in essence, what you want to do. Okay, actually it turns out Hölder is also okay. Yes, in the infinity it's sort of difficult to make a good analysis. So in some sense you would, of course you have Nash-Moser and so on, but ultimately you trick your way through by working with finite norms and doing certain things. So what I'm describing here, I'm pretty sure that there is some kind of Nash-Moser generalization of this as well. But the analysis which we do here is sort of as close as possible to the usual thing what you need to go through with this one. So it would cover elliptic problems on varying domains with varying targets. And varying domains here means the topological type can actually change. Like you have suppose you have a cylinder, the cylinder has a conformal structure, goes to infinity, and in the infinity you would have actually two disks with a node. Yeah, so So that's a possible generalization. So this thing here would be the limit of a cylinder with a standard conformal structure degenerating if it gets to infinity. So you want to cover these situations as well if you have maps on them. So now, of course, if you see this list of obstructions here where you are as far as possible from smoothness as you know it, yeah, then it's not surprising that the methods which were picked so far usually try to restrict the problem to a finite dimensional problem. Rather than working in a big space, you make finite dimensional reductions. Then you have an elliptic problem. If you perturb correctly, the solution spaces should be smooth but finite dimensional, and you can do a certain number of things. But it turns out, if you do it honestly and prove everything, like that the solution spaces are actually smooth and so on, then you more or less, since you have to perturb the stuff, as I said, these things are usually non-generic, so you have to perturb it. That means you have actually to define what a neighborhood of an object is, where you want to find the solution. Yeah? So there are a lot of things, if you honestly think about it, is actually you have to address, and you want to talk about smoothness, you have to address some of these things, maybe in a more ad hoc fashion, and maybe you can avoid certain things. But it's unavoidable. Some of these issues will appear if you want to put smooth structures on solution spaces, if they might contain, say, in Gromov-Witten, if in your solution spaces there are noded curves in them as part of unnoded curves, and you want to put a smooth structure on them. Since these things had to be perturbed, you already lost some control, which meant you have to understand a priori a much larger scenario to begin with, because the perturbed solution space can be anywhere. So you have to deal with some of the issues. So now, I think it's clear at this point that the things which overcome are this kind of nasty analytical things, where you have the actions by groups on the wrong side, yeah, on the domains and so on. So before I start on this, is that ultimately what we want to do is, there's still a little bit of work we have to do, but I'm pretty confident that we can do this, is that we have something what we call a black box theory, which means you only have to understand a little piece of analysis. It's done to certain specifications. It involves the construction of certain spaces, of certain bundles, and of showing that certain sections which are of interest are pre-Fredholm sections. The black box, in the black box you can view, it has inputs and outputs, and if you have another black box with a matching input-output, you can put two black boxes together, and you have another pre-Fredholm problem. And if there are some other things you can stick things in, you always get pre-Fredholm problems. If there's nothing to be sticked in anymore, it's a Fredholm problem. So, and you want to know, you want to give a specification and saying if you construct a black box according to these specifications and somebody else constructs some other black box with specification and it passes this test that it can be stick together, it's again a black box. The advantage of this is then that analysis can be recycled. If you look, that is one for those who work in the field of symplectic geometry. All the papers are usually extremely long and have gaps. So the reason is that at some point you're running out of steam and you say, no, you do it like in this and this reference. Where you then, if you look, actually, the author forgot that this person actually never did it but referred to somebody else. Who also, and then you maybe on some limit cycle of referrals, but nobody ever did it, yeah? So that is one of, and the papers are usually extremely long, and a lot of things are sometimes disputable. So what we want to have is, we want to show that there's a method of which tells you that there are basically no excuses. You make a small piece of analysis to specifications, and then you know it works with the other pieces which have been done to the specifications. So we can do this with the spaces and so on. I can do it for the Fredholm theory evolved in SFT, but I don't have a for the Fredholm. I don't have a good general pre-Fredholm definition yet. I mean, there are some definitions which would cover our applications. So that is still what we're working on. But it turns out that Gromov-Witten, from this point of view, is built out of two black boxes, understanding what happens in your two nodal disks, like this. And the other is a Riemann surface with a very complex structure and maps on it. So you can build this to specifications, you plug them together, and you can build of general nonsense in Gromov-Witten. And for SFT, you need an additional black box, which is essentially connected with gluing your periodic orbit. And you plug them together, and you can do this. So now, so I want to describe a little bit how to do that ultimately in this 8 hours. I don't know if I get there for Gromov-Witten. And then it turns out that it's also a good idea to think about it. Can one actually define smooth structures on certain categories? And the reason for this is the following. If you do symplectic field theory, or Gromov-Witten, and in symplectic field theory would be even more important, then the important object is a stable map. A map from a noded Riemann surface with certain property into the symplectic manifold. Of course, if you view this as an object in a category, this is a class. You know, there's too many of those guys. But then you define the notion of isomorphism between two things, and the stable map has a property that between two stable maps, if they're isomorphic in some way, there can be only finitely many isomorphisms. I'm going to explain this. So what you get is you get a category where the object space is actually a class, but between any two objects there are at most finitely many isomorphisms. But if you divide out by the isomorphisms, you get a set. Yeah? And it turns out if you look at all candidates, not just the holomorphic one, all candidates say in a certain Sobolev space or Hölder space, then this orbit space we divide out by all isomorphisms has in general a natural topology. So you have categories with a property that if you divide out by that every morphism is an isomorphism. Between two objects there are only finitely many isomorphisms, and if you divide out by the isomorphisms you get a set, and that set has a natural topology. Can you define on categories of this type a smooth structure? In some sense it should mean, you see, if you view such a category as follows, so an analog would be a set with a group action where the group orbit of a point is just the isomorphism class. And then, in some sense, up to some minor algebraic structure, which is however important, is that the orbit space identification is some kind of a slice locally. So that is sort of the picture. Yeah, and it turns out that this is actually very useful to try to define something like this for the following reason. If you do, for example, stable maps in symplectic field theory, then all the algebraic structure you ever care about already lives on the categories as functors. And then you just want to say that all these algebraic structures are actually smooth in some way. And the Fredholm theory is compatible with this, and so on and so on. And that then rather dividing out by isomorphism classes and then recovering some of the other structures which you just killed by exhibiting it later. Just want to say there's a category with a lot of structure, and all the structure is smooth in some sense. And you have another category over this, which over each object is a vector bundle, is a vector space, and you have a section of this. And you want to say a section functor of this, you want to say that section functor is smooth. Then you want to say this section functor is actually Fredholm, and then you want to have a perturbation theory by other functors, and then the solution set of this functor actually has a structure of a smooth manifold, say, in good cases. Yeah? And so that actually the zero set of a particular section functor is a full subcategory, or say is a full is a manifold in simple cases, or in other cases a full subcategory but has some smooth structure, which is enough to define some fundamental class and so on. So that is what you ultimately would like to do, and that what we, because I will explain that. Yeah.
There is something called some query by goodwill ground on the basis of functors.
No, I don't know. Okay, so let me now write down the series example, which is sort of the category which you would get from Gromov-Witten, on which then one can try to explain basically everything, but this kind of issues which are highlighted there are all occurring there in some way or the other, or versions of it. So is that so far? Okay, so let's now look. Let me write down the Gromov-Witten example. So it has all these difficulties in it, but it is, but in some sense, it has less algebraic structure like SFT. So now, you can, of course, do this by more ad hoc methods if you want. So, but if you go to SFT, where you have to make so many choices, in fact, infinitely many, any choice you do for perturbations imposes infinitely many other choices you have to make already. Symplectic field theory. So you have sort of enormous amounts. You have a countable family of interacting Fredholm problems, which are all non-generic. You have to make them generic, and then if you pick a perturbation somewhere, this perturbation influences what you have to pick as a perturbation at infinitely many other problems as well, and so on. So if you don't have a good language for this, it becomes a nightmare. So it's also a question of language. So now the objects, so I'm going to define the objects here, which already is a considerable list of things. And ultimately, you want to say that these objects are part of a smooth space in some way. Yeah. So every big object which takes 2 pages to define is a point X, yeah? In something else which has some properties. Okay, so now, so we have a symplectic manifold. So it's not important that it's compact, but let me assume it's compact, and I don't have to say anything. So then fix a number delta 0 between 0 to pi. So now you might ask, why do I define this? I have to specify certain exponential decay. That the number happens between 0 to pi is, since for me the unit circle S1 is R mod Z, and on this basis ultimately I have to do a Fredholm theory, and there is a self-adjoint operator minus I ddt on the unit circle of length 1 has a spectrum 2 pi Z. That is where it comes from. So fix a number there. And now here are the objects. S, J, M, du, which I'm explaining now. So Sj is a closed three-minute surface. I will draw you a picture. It might have different components. Then M in S is a finite ordered set of marked points. D are nodal pairs. So nodal pairs, so D is a collection of things like this, where X is different from Y. X and Y are points in S, but not marked points. And the property is if these two sets intersect, they're actually the same. So I draw you a picture in a second. So you would think of this as follows. So here is my this is my S. Okay, J is a complex structure on S. almost complex structure, smooth almost complex structure, giving the orientation. But it's a theorem which says that an almost complex structure is actually integrable on surfaces. Okay, good. So now, then my D here consists of pairs like this, for example. And you should think of them that these two things are being identified. Yeah? And here maybe we have x prime, y prime. And then we have the mark points which are different from this. Say that would be the first one, the second one, it's the third one, and maybe here is nothing on it. So this is what I explained up to this point. So this condition just means that you cannot identify this with that and this with another point. Yeah. So that's what I explained so far. Now comes U. So U has some regularity properties, which in particular imply it's continuous. So let me first say then that U is continuous. So at least at this point, I can say that U of x equal U of y for x and y, a nodal pair. Yeah, so at these corresponding points which you can identify, the value of the thing is the same. So then, secondly, now some regularity. U is in, you don't like Sobolev spaces, but I like them. So H3 log away from nodal points. So nodal points would be points in this thing here, which is just the union of these points in the set here. So if you're away from the blue points, it's in H3 log. And now I have to say what they do near the nodal points. Yeah? So near the nodal points, for every x, a nodal point, there exists a smooth chart psi from. So here, it's not a symplectic chart. It's just a smooth chart, and then I may assume it goes onto some R to n, yeah, where you map U of x to 0. So you map, so there's a smooth chart on a neighborhood of the nodal image, yeah, the image of the nodal point, which maps the nodal point to 0. And so that and positive holomorphic polar coordinates sigma around x. So I have this point x here. I take a disk-like neighborhood around this point x. So x is this nodal point there. I say what it does near a nodal point. Yeah? The pairs are nodal pairs. So two nodal points, the right ones together is a nodal pair. So I take a disk-like neighborhood of this. Then this is biholomorphic to the standard disk, and then to the standard disk I go by exponential minus e to the minus 2 pi s plus it, and compose it with a backward map to the disk. So I parameterize everything except that point here by holomorphic. This is positive holomorphic polar coordinates, sigma around this. And then, so that the map psi composed with U, composed with sigma of st, so you have this map. So you start on a, so in order that this all is defined, you need S for S large. This is well defined for S large. you're sufficiently close to x, but the sigma. If S increases, you go to the nodal point. Then you go are in the U, and then since this is a neighbor defined on a neighborhood around the nodal point U of x, you are in the neighborhood where that psi is defined. So now you have a map into R to n. And if S goes to infinity, this map will converge to 0 because the nodal point goes to the nodal point. So you want that this map, this belongs to H3 of sufficiently large thing here, cross S1, but with an exponential weight delta 0. So, or let me say that this let me write this here. So this weighted by exponential minus exponential 2 exponential delta 0s. So you put this weight on. Belongs to H3 of S0 infinity cross S1 R to n. So which means that you actually approach this nodal point with a certain exponential decay, including the derivatives up to order 3. So this here, this thing we call. So then there's a fourth property. The property is the following. If so for every connected component C of S, so this would be a connected component, this would be, so in this example I have 3. For every connected component C of S, we have the integral over C U star of omega is greater or equal to 0. Now, if you vary U, this integral will not change, because it's a closed form. But we have this, and if 2 times the genus of C, of the component, plus the number of special points in C, namely marked points or nodal points. So you look at all marked points or nodal points on C. So in this case, there would be 2 special points, the M1 and the X. Here would be Y, it would be 4 special points, and here would be 1 special point. So if 2 times the genus of the surface plus the number of special is less than 3, the integral U star we have is positive. This is called the stability condition. Yeah? No, just in the Sobolev space. I said this is called the stability condition. So if you have, so the thing is, if this number is at least 3, if you have, view this as marked points here. If you have on a Riemann surface enough marked points so that the 2 times the genus plus the number of marked points is greater or equal to 3, then you have only a discrete set of automorphisms keeping these points. And what it says is if there are not enough marked points on this thing compared with the genus, then we need the integral to be positive. So this is the precise condition, and we say, so if this is all true, we call a stable map of class 3 delta 0. Yeah? Well, if I would look at solutions of the Cauchy-Riemann equation, they would all be 0. There would be any. Well, you can put that in if you want. So now, let me, and then I stop. Let me now define no, it does not depend on this. This only depends on this choice here. So let me give this a simple name, sigma. The what?
By S, number 3.
Where is S?
Number 3.
Number 3, yes.
S is the negative log of array. And T is the
Oh, yes, so T is in S1 and S.
S is the negative log of array.
Yes.
So it's not exactly coordinate.
Holomorphic coordinates around X, which by my definition, of course, exclude X. It's clear?
Can you call sigma not two different?
What is sigma? What else?
Sigma is your polar coordinate.
Yeah. Okay, so that was a joke. Okay, so now, so let me say so a morphism between this guy. So let me call this Tor then. So I want to view these guys as objects of a category. So I define now. So this would be the same letters but primed. Yeah. So what is a morphism? The morphism in this category of isomorphisms is, of course, where phi is a biholomorphic map biholomorphic. So that means it has to preserve the ordered M's, and it has to, of course, will map nodal pairs to nodal pairs. Biholomorphic map so that U prime composed with phi is U. That's a morphism. And of course, it's invertible. Yeah, just interchange these two letters here, put phi inverse. The domain is Tor, the target is Tor prime. You can compose them. So now we get, we have a category. And this is the category of stable maps of class 3 delta 0. And the category, the objects are these 5 letters in a bracket. The stable maps and the morphisms are these guys. The category has the following property. If you divide out by the isomorphisms, this is a set. So what is not visible here, but which is true, is it has a natural topology for which the unknowed things are open and dense. The class is generated by. So this thing here is in fact has a natural metrizable topology determined by the choice of 3 and delta 0. So now, this requires some proof. You're not sitting down doing 15 minutes. But you can imagine what that should be. For example, neighboring classes, if you just keep this here fixed and change the U a little bit in H3 delta 0, that should be close by. The only difficulty which you would have is if you remove a node. I have to say, if I remove nodes, and then how should the maps between nodes behave so that they are in the neighborhood of the noded one? Yeah. So, in any case, this has a natural metrizable topology. Huh? Metrizable is Hausdorff, I thought. So that the equivalence classes of unnoded ones, unnoded objects. An unnoded object is one where the D is the empty set, where there are no nodal pairs. So that the class of unnoded objects is open and dense. So then also what we observe is this follows from the stability condition. So this is, Gromov proved this compactness theorem, but his compactness theorem is actually literally not a compactness theorem because the topological space he constructs is actually not Hausdorff. So then Kontsevich observed that one has to add a condition, namely that is the stability condition, and then if you then redo Gromov compactness for the pseudo-holomorphic curves, you get a Hausdorff space. So now between, and the Hausdorffness comes from the fact that, it's also not that apparent immediately, is that if you look at the automorphisms of an object here, then the automorphism set is finite. And the set of isomorphisms between any two objects is always finite. That is due to this condition here. So, and between any two objects, there are only finitely many morphisms, and all morphisms are actually isomorphisms. And they are all isomorphisms. So these are particular, so I call this a topologized groupoidal quasi-small category. So I don't know what the right word is here. So a groupoid is a category where which is a small category where object set and morphisms are sets, and every morphism is an isomorphism invertible. So then, is the case here. So then, but it's not a small category here. It's too big. So then I would call it quasi-small. Yeah. So we have categories where all the morphisms are isomorphisms. They're between two objects, there are only finitely many. If I divide out by them, I get a set, and the set has a natural topology. So for these things, actually, one can define a smooth structure, or the smooth structure on such an object, as it turns out. And then let's make a break here. The next thing is I can define another category which lies over which fibers over this category, where over an object lies a vector space, which has 6 letters, the elements, another one, and the Cauchy-Riemann section, but you need the choice of an almost complex structure for this, and the Cauchy-Riemann is a section functor of this. And then ultimately, there's a smooth structure of this, there's a smooth structure for bundle of this, and for the smooth structure, the Fredholm section is smooth, and it's even better, it's a Fredholm section, and you have some abstract nonsense you can throw at it. It makes transversal. And then the solution set, in good cases, would be a full subcategory of this, but it has compactness properties and so on. And locally looks like a manifold, but you have these morphisms and so on. And at complicated points, which are multiple covered and so on, you have it's some kind of a finer object. It's a full subcategory, but where the objects also have weights, rational weights. The problem is that you have certain symmetries, and you have all these morphisms. Morphisms are, of course, poison if you want to make things generic, if you want to keep the structures. Because at certain points, if you would have an object in the solution set, you would have a, say, non-trivial representation on the kernel of some group. And then if the index tells you then it's not onto anymore, the operator, then obviously it cannot be a generic point. So you have to come up with some other properties. So you have to break the symmetry. Of course, that's bad. But then when you break the symmetries, you introduce more problems of similar kinds so that the whole family of local problems is invariant under the symmetry. And then you have to assign to the local problems weights so that the sum of the weights is 1. Then if you start with a generic situation, perturb a little bit, and replace it by a larger number of close-by problems so that the sum of the weights of problem, the counting is still the same, but it resolves the issue at the bad points. Okay, so let's make a break here, 15 minutes. And then, too long?